Hello again everyone, welcome back to ptet.chemistry channel. So this is Mr. On. So this is the second video of this 10 video series on just these infographics that are released by Cambridge Assessment International Education. So that's CAIE, that is the examination body that actually provides examination for Cambridge International A-level chemistry, okay? In addition to OCR and other stuff as well. So during the COVID pandemic, so they made a bunch of materials free on the Resource Plus, which usually we have to pay extra money for them. So this is one of the excellent materials that they have provided, which I think are really neat, and that's why I'm sharing them with you. So these are available in a Google Drive folder in the link on the video description, which you can download and use as you please. But again, these are just infographics. These are not your complete curriculum specifications. Yeah, it merely shows you how the stuff are linked together. All right, whether you're a beginning learner or whether this is a good summary or not, I leave that for you to decide. And you can always check my other topical playlists for the A-level topics if you're unsure about anything. All right. So bonding and structure, or like I call it structure and bonding, as I normally would say, is that it's a very important concept ever since you did it in O-level or the 14 to 16-year-old stages, wherever you are in the world. So you see this structure here, it represents a giant ionic lattice structure. What you draw on paper is usually like that, but they do not exist as just one single unit. They actually have a giant lattice network, meaning they're repeated with a nice array. Here you can see the sodium depicted in gray there is surrounded by 6 chloride ions, and each chlorine in turn is surrounded by 6 sodium ions, etc., etc. And it's the attraction between the cations and the anions that give you the strong ionic bond. Whereas if you talk about covalent bond, we also talk about something called dative covalent, or can be termed as coordinate bonding. So they are different from the normal covalent bond because of one of the atoms donating both the electrons using the covalent bond, whereas a normal covalent bond involves equal sharing of electrons between the two atoms that form the covalent bond. So covalent bond is directional, and you can count them. You can count 1, 2, or 3, unlike ionic bond or metallic bond, which are not directional. You cannot count them. They are merely like force field. And yes, covalent bonds are directional, but they're essentially also similar to like a force field. You have your bonding electrons there. They are negatively charged. They are attracted to the nucleus or both the nuclei here. The nucleus contains the protons, and these protons attract these electrons involved in bonding, and therefore it leads you to that electrostatic force of attraction, which is the covalent bond. Okay, so you can have simple molecules like this where you are not actually breaking the covalent bonds when you change their state from solid to liquid or liquid to gas. Very important and very confusing with these things called giant molecular structure. So this is a structure of diamond, or this is a structure of graphite. So these are giant molecular structure, and this will involve breaking the covalent bonds. In fact, many of the covalent bonds when you try to change their state from solid to liquid or liquid to gas. All right. Whereas for simple molecules like C16 here, or water, or CH4 or PCl5, so they all have different shape, and those are covered under VSEPR. So a lot of students don't even know what VSEPR stands for. It stands for valence, meaning the outermost, shell, electron pair repulsion theory. And this theory allows you to predict the shape of molecules of ions, So it means that if you don't know about VSEPR, you're not talking about electron pair repulsion, basically bond pair or lone pairs, you don't know how to count them. You're not going to do shape of molecules or shape of ions very, very well. Okay, so you gotta know all those, and you can check out the topical playlist for how I cover them, all right? Because they can affect the strength of your intermolecular forces depending on your molecular polarity. So very common in multiple choice question, for example, yeah, where they try to trick you. Then you have this metallic bonding, where metals, when we talk about metals, So metals are elements, and you should know the definition of elements being only one kind of atoms, all right? And in metals, you only have one kind of atoms, and the metals can shed their outer shell electrons, so they can delocalize their outer shell electrons. So these are not anions, these are the outer shell electrons that get delocalized, and that's why the factors affecting metallic bond include how many outer shell electrons can you delocalize. Are you a group 1 metal? You delocalize 1 outer shell electrons. Are you a group 2 metals? You delocalize 2 outer shell electrons. Are you a group 3 element? Therefore, you delocalize 3 outer shell electrons. And in doing so, you will have different charge on your cations. So there's another factor that can affect the strength of metallic bonding. And then you also have different sizes of your cation, because as you know about atomic structure in the other series, in the first video series where you talk about nuclear charge, shielding, and effective nuclear charge, we talk about atomic radius decreasing across a period, and the cations are smaller and the anions are bigger than the respective atoms. But across a cation from sodium plus to Al3 plus, they still get smaller, and your charge gets bigger, and you delocalize more and more outer shell electrons. They go from group 1 sodium to magnesium to aluminium across the third period, and therefore your melting point of your metals across the third period from sodium to magnesium to aluminium would increase. Again, that's to do with melting point. It has to do with your nuclear charge, your shielding, your effective nuclear charge, okay, which affects your structure of an atom. And but when we talk about melting specifically, we talk about the structure and the bonding. What are we breaking, and the factors affecting the bond itself? Yeah. Again, there's this thing on. What have they done here? Let me think. So there's C60, which is a simple molecules, and there's just carbon nanotubes. It's just single layer of graphite being rolled up, and because it's a single layer of graphite, it still has giant molecular structure. So carbon nanotubes should have similar properties like graphite, should be able to conduct electricity, should be very light, and again should have very high melting and boiling point because it's giant molecular structure like that. Yeah. Okay, so this is what I meant by you should be able to specify the lattice structure. Is it giant metallic? Is it giant ionic? Is it giant molecular? Is it simple molecular? Okay, and therefore what are you breaking? Those are very important when you try to justify physical properties like melting point or boiling point. All right. Then they talk about liquid state. So a lot of things in the liquid state are not talked about very much, but you should know that in the syllabus there's something called vapor pressure. So have a look in your specification. You can think about vapor pressure being the liquid particles or liquid molecules being in equilibrium with the gaseous molecules or gaseous particles. All right. So the difference between evaporation and boiling is something to think about as well. Yeah. And of course, you get all these bonding and physical properties, which result in conductivity, electrical conductivity, melting and boiling point, solubility in water, volatility. It's something to do with boiling point. So if something is more volatile, it boils easier. And therefore, it means if something is more volatile, the boiling point is lower. So a lot of students, they cannot comprehend or understand the meaning of volatility in terms of boiling point. When something is more volatile, it boils easily, it has lower boiling point. All right, so all that could be explained by structure and bonding. Then there's this property of gases where you need to think about PV equal to nRT. This is very, very important and usually involve a couple of marks in calculation. So they only define it by the definition of the quantity of the unit, quantity of the measurement, the physical meaning. Okay, but they didn't mention the unit should be in Newton per meter square, which is equal to Pascal. So 1 Newton per meter square is equal to 1 Pascal. So you gotta understand this is the SI unit, and if you are given in Pascal, it's the same as the SI unit there. Okay, the volume is in meter cube, has to be in meter cube. Yeah? The number of mole, which you can express as mass over mR, that is gram per mole, which will give you overall mole. Okay, the ideal gas constant, which you get from your data booklet, It's joule per Kelvin per mole. And the temperature has to be in Kelvin, where any temperature in degrees Celsius, you convert it to Kelvin by adding 273. I hope you know that, yeah? I mean, by this stage, you should probably know that already. This is the key confusion for a lot of people. I'm going to just show you one example. If you are given in cm cube, what is that in meter cube? All right, you should be aware that 1 cm is equal to 10 to the minus 2 meter. There's 1 over 100. Okay, if you cube both sides, you will have done the same thing on the left and on the right. Therefore, 1 cube is 1, cm cube is cm cube, 10 to the minus 2 cube is 10 to the 6, meter cube is meter cube. I never tend to remember these things, and here I've just shown you how to get the conversion factor from 1 cm cube to become 1 meter cube. And of course, if you're already given a meter cube, you don't need to convert it, but question can give you in cm cube where you need to convert it. You can try the same with dm. 1 decimeter is 10 cm. So 1 decimeter is 10 to the power minus 1 meter. So 1 decimeter cube is equal to 10 to the power minus 1 meter cube. So 1 dm cube is equal to 10 to the power minus 3 meter cube. Some students, they tend to memorize this by heart, sometimes they get confused, but you can very easily work it out with your elementary mathematical skills. All right. Then there's this thing under bonding that's called electronegativity. It tells you the idea about molecular polarity. This idea about dipoles, we call them delta plus, delta minus, where the electrons are not exactly localized in the middle. In fact, they are localized, or we say they are located, because they are not delocalized. They are localized electrons. They are localized closer to the more electronegative elements. So fluorine is very electronegative. It decreases downward. It's the most electronegative element in the whole periodic table. It also decreases that way as well. But among the first raw elements, so fluorine, oxygen, and nitrogen, these three are the most electronegative elements in the whole periodic table. So when you have a hydrogen, when you have hydrogen bonded to H or oxygen or fluorine, and you have a lone pair on any of these, you can get hydrogen bonding. And in general, okay, just in general, hydrogen bond is stronger than permanent dipole. It's stronger than van der Waals. Okay, this is just a general trend, and there are some cases, especially when you talk about the boiling point of HCl versus HBr versus HI, you will realize that even though the permanent dipoles are getting, you realize that it's actually the van der Waals that are more important than the permanent dipole, which will give you the opposite trend to what you actually see for the actual boiling point of these hydrogen halides. So you can get examples of this kind of questions in the topical playlist for group 17 chemistry under A-level chemistry, so you can see a couple of examples of what I mean when you go through those questions. All right, so what have I done here? I have not done much really. So a lot of gibberish talk, where we started off talking about I don't know, bonding. Okay, so how the atoms bond together, what are the force of attraction between the electrostatic force of attraction, meaning something positively charged and something negatively charged, yeah? Okay, and what do you need to break in order to go from the solid to the liquid state that is melting, in order to go from a liquid to the gas state that is boiling. And then there are other bonding and physical properties, and there's this thing called electronegativity, which come as a result of your atomic structure. All right, so you talk about nuclear charge, your shielding, and your effective nuclear charge in the previous video, the first one of the series. That's how you explain atomic radius. That's how you explain ionization energy, and in fact that's how you explain electronegativity as well. But that is not how you explain melting point, because melting point has to do with solid to liquid. That's to do with structure and bonding. What is the structure? What is the structure, and what do you need to break? Very important, yeah. The ideal gas equation usually come up as a manifestation of the various gas laws, including the Boyle's law, including the Charles law, including the Avogadro's law, and then they all manifest as this ideal gas equation, which comes along with it assumptions of ideal gases. And obviously, like if you break the assumptions, the most important of which is you have more and more stronger intermolecular forces under certain conditions, like high pressure or low temperature, then you're going to break the ideality a bit more, you're going to challenge the equation a bit more, it's going to follow the assumption less well, because you're breaking the assumptions. So that's it for me in this video. I hope that gives you a flavor. It might not be that helpful, but yeah, I mean, if you want more details, you can always look up the other topical playlist. Yeah, so I'll see you in the next video. Thank you for watching.